Okay, we are back, and what did we do? We took an arbitrary complex number, and well, it wasn't too arbitrary. I picked it specifically. 2 plus 2i. The x and the y component are both 2, so I know that the tangent is y divided by x is 1. I know that when the tangent is 1, it's 45 degrees. I wanted to use something that was recognizable. Basically, what we did was we have this vector. It's at an angle. It's telling us it's going a direction. This happens to be a two-dimensional vector. And so the x component is going this way. The y component is going this way. The vector is when you add these tails together. And we're not technically at vectors right yet. I got a lot more to talk about. But this really becomes a beautiful correspondence. And let me go back to some amazing things now. Unfortunately, at the level in this class, I can't prove this to you. This requires, we usually prove this in Calculus 2. And you're not there. So unfortunately, you have to take my word. And this is always unfortunate. It's much better if you could prove this or watch the proof and go, yes, I know that's true. We can expand e to the x like this. It can be shown that e to the x can be written as this: 1 plus x over, I'll put up the exact formalism, plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus dot 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 plus, in the general form it has this, x to the n over n factorial, and it keeps going. It's an infinite series. Taylor series, one of the things you'll see in Taylor series are infinite series. Incidentally, 0 factorial is defined as 1. We're not dividing by 0. And in general, n factorial is just n times n minus 1, n minus 2. I'll give you an example of this. It's so unfortunate. A lot of people don't see these notations. 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, etc. You'll notice they get big very fast. Also, beyond the scope of this class is it turns out for every value of x, this infinite series converges. Okay. I also showed you in one of the previous lectures that by the same Taylor expansion you can find, the same technique, that cosine x is 1 minus x squared over 2 factorial, and this is really 1 over 0 factorial. I guess I'll write it in to be precise. Plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. This just keeps going on in this exact same pattern. I think you can see it. And sine of x is going to be x minus x cubed, and this is x over 1 factorial. 1 factorial is just 1, which is, so 0 factorial is 1, and 1 factorial is also 1. Over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. I'll do one more, plus x to the 9 over 9 factorial. Goes on and on and on. Also, beyond the scope of this class, for every value of x, these infinite series converge. Basically what that means is, for all the numbers, all real numbers, we have these converging properties here. Now I would, basically this will work. So e to the box, whatever it is, this is going to be, we just replace the x with a box. All right, whatever goes in the box, these are going to be the same thing. And I want to do this. I'm going to toss a little I in there this time. So e to the ix is going to be this. So ix squared. So what is ix squared? It's going to be I squared times x squared, but I squared is negative 1. So this is going to be minus, I'll put the little minus here, x squared. ix cubed, we'll do this, driving my producer crazy. Ix cubed, this is the same as I cubed, x cubed. I cubed is negative I, so this is negative I x cubed. And I to the 4th I x to the fourth will be I to the fourth, x to the fourth. I to the fourth is 1. This is going to be 1 times x to the fourth. So I guess I'm not going to do too many more. I'll ask you to accept this on faith. But it turns out that e to the ix is equal to, look at what we have here for cosine. This, this, and this. You'll notice these terms are the first 3 terms of cosine x. And it works out all the rest of them as we go. So basically, half of this, so to speak, is cosine x, right? What's this? I to the x minus ix to the cubed. It's going to turn out that this is the same, this part, these other ones are the same as I times sine x. So here's the fascinating thing. It turns out that e to the ix is equal to cosine x plus I sine x. This is huge. Yeah, it's hard to say. Depending on who's teaching your class, they may or may not insist that you know where this comes from. You're going to have to use this, though. I saw that they presented this in the books, and also, incidentally, they usually use theta. So here's e to the I theta equals cosine theta, I sine theta. Okay, so this is pretty fascinating stuff here, and I'll show you why. I'm going to have to erase some things. The great physicist, now unfortunately passed on, Richard Feynman, when he was a young man, said, like many people who first discover this formula, that this is one of the most exciting things in all of mathematics. I know you may find it hard to believe that some of us really get excited about this, but so think about what this means. What does e to the I pi equal? Well, so in this case, theta is pi, so none of my markers are as brilliant as I'd like today. According to this formula, this is going to be cosine pi plus I sine pi. Now, cosine pi is equal to -1. Sine pi is 0. So e to the I pi is equal to -1. Or, this is the same as e to the I pi plus 1 equals 0. And why so many of us think that this is one of the greatest equations in the history of ever is because this has 5 of the most important numbers in mathematics. 0, 1, pi, I, and e. All of these numbers are magical in many ways that unfortunately I can't go into greatly because you'd probably die of boredom if you don't love math. But so what does this have to do with figuring out stuff in the complex plane? Oh, and let me do one more thing too. So you know that you have this right here. What happens if you do, get some space. So we have this, e to the I theta is equal to cosine of theta plus I sine theta. Why was this so important? Well, when we put these points up here, this complex plane right here, remember when we did 2 plus 2i? Here is the modulus, and we're going to call this r. This was the norm of 2 plus 2i, and norm and modulus mean the same thing. And this is equal to the square root, 2 times the square root of 2. What did we figure out? Well, so we figured out that alpha was pi over 4 in this particular case. Oh my goodness, we're running out of time so fast. We're going to have to switch up here pretty fast. Well, what did we figure out? We figured out that the cosine of pi over 4 was equal to, or r times the cosine of pi over 4 was equal to the x component, which is 2, and r times the sine of pi over 4 was equal to the y component, which was 2, but it didn't be 2i. What we need to do this is write this as r times I sine theta to get 2i. So in general, r e to the I theta equals r cosine theta plus I sine theta. We got to come back. I'll be right back.